Well, it's been a while since we've had a little chat about chemistry here. I hope you had a good break, and I hope you enjoyed the Natural Easter Egg Lab. I know one reason I assigned that is because my family has a tradition of dyeing Easter eggs naturally. Uh, and it goes back to at least my great grandmother. I know that she dyed Easter eggs using yellow onion skins and passed that tradition on to my grandmother and my mother. And I have dyed Easter eggs using red cabbage juice. So I hope you enjoyed that. And I know one student at least shared with me that her family also has a tradition of dyeing Easter eggs naturally. Well, we're moving on to chapter 10. And chapter 10 is one of my favorite things. It's talking about gases. I really like the gas laws, and I just think it's a good chapter because it describes it, the why a lot of things happen with gases that we observe in nature. And I just hope and pray that it will give you a better appreciation for gases and God's genius in how He made gases and how gases behave. So, we are going to be studying chapter 10, gases, and we're going to start out by talking about the properties of gases. So, what I'll do is I will show you the notes for this first part, section 10.1. And just pause your video and jot these notes down, and then I'll talk about them. So the first thing we have to have an understanding of if we're going to talk about gases is we have to know about the kinetic molecular theory. And the kinetic molecular theory is how we describe the behavior of gases. And there are a few assumptions that are made when we use this theory. And so we're going to talk about those 5 assumptions right now. The first assumption is that gas particles are tiny compared to the great distances between them. And to give you an idea of how small they are, if we were to take a molecule of oxygen and we were to make it the size of a bumper car, okay, we took a few molecules of oxygen, made them the size of bumper cars, those bumper car oxygen molecules would be 20 miles apart. Okay, so that is how big the distances are comparatively between gas molecules and how close they are to one another. So they're pretty far apart. The second assumption is that particles move at random with high velocities in all directions at many different speeds. So not all particles are going the same speed. They are basically like marbles bouncing all over the place. They're going in all kinds of directions, just bouncing around at random. The third assumption is that these particles do not interact with each other or the walls of their container except during momentary collisions. And at 0 degrees Celsius, that means there are 5 billion collisions per second with the particles. And this means if we're assuming that there are no interactions, we're ignoring gravitational, electrical, and chemical forces between these particles. So that is an assumption we are making. The fourth assumption is that collisions between gas particles conserve energy or elasticity. This means that when they collide with one another or the walls of their container, they do not lose any energy, and that is a property called elasticity. And the fifth assumption is that the average kinetic energy of the gas particles is directly proportional to the temperature of the gas in kelvins. Remember, Kelvin is a temperature scale, and Kelvin goes down to absolute zero. This is so that we do not have any negative numbers. All of our calculations that we talk about are going to be in Kelvin, not degrees Celsius or degrees Fahrenheit. So let's take a look at how we can use these assumptions as we talk about some properties of gases. And we'll be referring back to these assumptions quite a bit. So here is section 10.2, the physical properties of gases. Go ahead and copy down what I have here, and I'll give you a few seconds and then I will move this up. Okay, so some properties of gases are, first of all, they have very low density compared to solids and liquids. And this goes back to the first assumption of the kinetic-molecular theory, that they are tiny and compared to the distances between them. Remember, density is a measure of how packed something is together, how packed the particles are. And so if you have really small particles that are spread out really far, it's a very low density. Just think of that bumper car. The bumper cars 20 miles apart. They are not very densely packed. So that is the first property. The second property is diffusion. Gas molecules move constantly and uniformly fill their container. This is why if a container of ammonia or perfume is opened across a room, you will eventually smell it. The gas molecules will diffuse and spread throughout the room. A property very closely related to diffusion is effusion, which you probably have not heard about before. Effusion is when a gas moves through tiny openings into an evacuated chamber. This is a lot like, think of a balloon with the end. If you untie the end, the air goes through that opening into the rest of the room. Okay, it's similar to that idea. And the gentleman who came up with this is called Graham. And Graham came up with a law called Graham's law of effusion from studying effusion. And he said the rate of effusion for a gas is inversely proportional to the square root of its molar mass. And the rate of effusion is inversely proportional to the square root of the molar mass. That's why molar mass, the square root, is on the bottom. Because what happens is as molar mass goes up, the rate of effusion goes down. That's what an inverse proportion means. That is, one quantity goes up, the other goes down. So we can actually make a ratio of the rate of effusions for two different gases. And that is using this equation here. Rate of effusion for gas 1 over rate of effusion for gas 2 equals the square root of the molar mass of gas 2 over the molar mass of gas 1. Notice 1 over 2 here, 2 over 1 here. That's that inverse proportionality. So let's do a problem using this. And let's calculate the rate of effusion rates between nitrogen and argon. So I'm going to abbreviate the equation a little bit. I'm just going to put RE for rate of effusion of N2 over RE argon equals the square root. Now remember, we have to flip them. They're inverses. The molar mass of argon over the square root of the molar mass of nitrogen gas. Now that N2 is important because nitrogen is a diatomic. So where do I get these numbers? I go back to my periodic table, and the molar mass of argon is pretty straightforward. It's 39.95 is what I'm going to use because we're going to round off to 4 significant digits just to make our calculations a little less cumbersome. So I have 39.95 grams per mole over the square root of, now don't forget that 2 times the molar mass of nitrogen, which is 14.01 grams per mole. So when I take the square root of this number that's almost 40, I get 6.320 over the square root of 2 times 14, which is about 28, which comes out to 5.293. Now when I divide those numbers, I get 1.194. Now don't forget, 4 significant digits here, 4 significant digits there. What this means is that nitrogen gas effuses 1.194 times faster than argon gas. And when we take a look at this, the larger the molecule, the more energy it takes for it to move faster. So that's why the smaller gas molecules move faster than the larger gas molecules. So let's keep going here and take a look at some more properties of these gases. So I'll give you a chance to copy this down and then I will talk about these. Okay, so we have 4 properties left. Permeability. This means that a gas easily mingles with another porous substance. For example, cell membranes. We have talked about in biology that cell membranes are semi-permeable. That means some substances are allowed to go through pores in them. Okay, we did a lab with dialysis tubing, and we saw that they had little pores that allowed sugar to go through them. And also you can observe this with latex balloons. Have you ever noticed that you blow up a latex balloon and say with helium, and you leave it overnight and the next day they're droopy? That's because some of the gas, the helium gas, has gone through tiny little pores in the latex and escaped. So that is permeability. Gases are a fluid. That means they flow and take the shape of their container. Liquids are also fluids. Solids are not. Gases show compressibility. That means that high pressure can squeeze gases into a smaller volume. We use this all the time with tires. We put gas in them, we squeeze that gas in there to make our tires harder if they've gone soft. We can also see that gases have expansibility. A gas quickly expands to fill a low pressure region. Gases go from high pressure to low pressure, and if we get, say, a hole in that tire, the gas will escape and it will expand. Okay, so what I want you to do now is I want you to turn to page 248 in your textbook, and I want you to take a look at those questions really fast and see if you can answer those questions. And I am going to explain the first four. So page 248 and 249, 1 through 4. And so turn off your video, take a look at those, see if you can answer those. And after you've done that, here are the answers. I'll give you a few seconds to check your answers, and then I will go over them and talk about them. Okay, so question number 1 on page 248 says, why can you smell a cake baking in the kitchen when you are in your bedroom? That is because gases diffuse and spread out to fill the entire volume available to them. A lot like the ammonia and the perfume that we talked about. That can also happen with the smell of food cooking. Number 2 says, how does the kinetic theory explain how you can smell coffee and bacon at the same time? This is because the gases both diffuse and are permeable. They're diffuse and permeable, meaning that one gas has the ability to mingle with another porous substance to fill an entire volume. So the porous substance they're mingling with is just the other gas here. So that explains why you can smell both of them at the same time. Now the problem here, number 3, it says, calculate the ratio of the fusion rates between helium and radon gases. So what I did for number 3 is I wrote down my equation, Re helium over the rate of effusion of radon equals, remember that inverse proportionality, so it's on the bottom here, but it goes on the top here. So the molar mass of radon, the square root of it over the square root of the molar mass of helium. Now I get those numbers from my periodic table. Molar mass of radon is, right here, 222. So the square root of 222 grams per mole over the square root of the molar mass of helium, which is 4.003. Now I didn't do this on the other problem, but those cancel out. That's why there are no units on this number. And so when I take the square root of those and divide, I get 7.45. This means that helium, being much smaller, having a lot less mass than radon, will effuse at a rate almost 7.5 times faster than radon. So much faster because it has a lot less mass. And then number 4. The question is, why is the carbon dioxide gas that carbonates fountain drinks stored in sturdy canisters? This is because gases are compressible and they can be forced under pressure into much smaller volumes. So that gas is compressed. And metal is used because it has enough strength to keep the pressurized tank from rupturing. Other materials cannot withstand that pressure, but metal can. Okay, at this time, I would ask you to go ahead and do that homework problem on page 270, number 1. And instead of a separate video, because it's not a very long problem, what I'm going to go ahead and do is just ask you to pause this video where it is, do your homework question, and then come back and check your answer. So go ahead and pause. And now that you're back, here is the answer. So page 270, number 1, says, use the kinetic theory of gases to explain why A, air has a low density. It has a low density because the molecules are far apart. We said that they're not. Density is basically a measure of how closely packed things are together, and these molecules are really spread out far apart. B, on a day with no wind, you can smell a dead skunk that is 500 yards away. This is simply because gas molecules diffuse. They will fill up the space that they're in, and after a while you will smell that stinky skunk. C, a large volume of air can be pumped into a small bicycle tire. This is because gases can be compressed because there are large distances between the molecules. So we can press those molecules together because they do have such large distances between them. And D, your egg salad sandwich can be smelled even through a sealed bag. This is because gas molecules effuse through tiny pores in the plastic. They're so small you can't see them, but plastic bags do have small pores in them. In biology, when we did the experiment with the dialysis tubing, where we put the sugar and the starch and the iodine in there, we could have used plastic bags instead, plastic sandwich bags, and they would have worked just as well as the dialysis tubing because they have small little pores that, very small molecules like gas molecules can travel through. So this is the conclusion of sections 10.1 and 10.2, and I'll be back with another video for you tomorrow. Have a good day.